This is Soup Lab 3. My name is Ethan Pickett. There are two main goals in this lab. The first is to demonstrate the effect that position and orientation of a magnet has on its magnetic field, on the strength of its magnetic field. The second is to determine a procedure to calculate the magnetic dipole moment of a magnet. This experiment demonstrates the magnitude of the magnetic field present is inversely dependent on distance, with the total field present theoretically decreasing by 1 over the distance to the third, and in our experiment decreasing by 1 over the distance to the 2.6. The mu value that we calculated in this lab is 4.2625 amp meters squared. Some core concepts for this lab. Parallel fields are twice as strong as perpendicular fields. In this lab, we'll refer to them as axial fields, or on the axis. The equations for the fields are present here. Fields that are at a specified angle in from the axis can be found using the following equation. And then mu can be calculated by this equation here, or by using algebra to pull the mu values out and solve for these mu values here, as you will see me do later. The procedure for this lab is fairly simple. First, I align the sensor with the Earth's magnetic field by finding the orientation that results in an approximately 0 x component in the magnetic field when the magnet is far from the magnetometer. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. At my location, the net magnetic field is approximately 49.3 microteslas. Then I position the magnet so that the x component of the force is equal to around 20 microteslas, and then noted the distance from the magnetometer. I then repeated this procedure 3 times. I then repeated the aforementioned procedure for 70 microteslas, 120 microteslas, 170 microteslas, and 220 microteslas. According to my results, my N value is roughly -2.6. It should be closer to -3. I assume this in my further calculations. My K value is found through the algebra of ln of K is equal to -14. K is therefore 8.31 e to the -7. Using this, we can find what our mu value is. If we assume that r to the 2.6 is equal to r to the 3, which we should, we can now find mu through simple algebra and find that mu is equal to 4.155 amp meters squared. To find the experimental mu value that can be calculated using the off-axis, we need a different equation. Using the off-axis equation above, and the knowledge that the off-axis magnetic field is 1.42468 e to the -5th teslas at 0.3158 meters, we can use algebra and this previous equation here to find that the mu value is equal to 4.37 amp meters squared. This is very close to our previously calculated mu value. I used this equation to create a computational model to model the magnetic field at different locations and orientations. You can see that the largest is the axial one, and the smallest is the perpendicular one, and the off-axis is somewhere in between those two. I also used an averaged mu value between the off-axis one we calculated and the other one we calculated to get a more accurately calculated experimental value. In conclusion, if I hadn't oriented the magnetometer so the x component is 0, then the x component of the magnetic field would have been either too negative or too positive and would have thrown the calculations off. If I stuck two of the identical magnets together, I would expect my calculated magnetic fields to be twice as strong. In order for this to occur at the same distances, the mu value must be double what it was. We concluded that the mu value of the magnet should be calculated to be around 4.2625 amp-meters squared. We also found that the strength of the magnet is inversely proportional to the distance raised to the power of 3. Since our value was around 2.6, we had a percent error of 13.33%.